Welcome to Formula 1 Maths. This is exercise 10.3 for GCE A-Level Applied Maths, Year 1. Exercise 10.3 is on forces and acceleration. We've got 3 questions to answer. Question 1. A trolley of mass 75 kilograms is pulled from rest along a straight horizontal path in a straight line by means of a horizontal cable attached to the front of the trolley. It accelerates at a constant rate, and after 3 seconds, its speed is 2 meters per second. As the trolley moves, it experiences a resistance to motion of magnitude 35 newtons. Find A, the acceleration of the trolley, B, the tension in the cable. So let's do a sketch, which is always advisable. This is a trolley, and this is a straight horizontal path. There are some forces acting on the trolley. The first one is the tension in the cable, which we call T. There's also a resistance to the motion of 35 newtons. There's a weight, 75G, and because there's a weight of 75G, there will be a normal reaction R. Because the trolley is not moving up or down, we're not going to use the weight and normal reaction in our calculation. The weight and the normal reaction do not also affect the horizontal motion. So the 2 forces that we're going to use in our calculation are the tension and the resistant force. The particle starts from rest. So our initial velocity, U, is equal to 0. And in a time of 3 seconds, it reaches a speed of 2 meters per second. We are asked to calculate the acceleration. We've got U, we've got T, we've got V, we're looking for A. So for A, the silver equation that we're going to use is equation number 1. So V equals to U plus 80. We do our substitution, and we get 2 equals to 0 plus 3A. Rearranging and solving gives us acceleration is equal to 2 over 3 meters per second. For B, we're going to use Newton's second law of motion, which states that F equals to ma, where F is the resultant force. And the resultant force in this case is the tension minus the resistant force. So F is T minus 35. And that will be equal to the mass, which is 75 kilograms, times the acceleration, which we found to be 2 over 3. So we have F equals to ma, we have T minus 35 equals to 75 times 2 over 3. We can reduce the fractions. 3 goes to 1, 3 goes to 25. And so the whole equation reduces to T minus 35 equal to 50. Rearranging will give us T equals to 50 plus 35, and solving gives T equals to 85 newtons. So that's question 1. Question 2. A lift is lowered or raised by means of a cable attached to its top. The lift contains passengers whose total weight is 400 kilograms. The lift starts from rest and accelerates at a constant rate, reaching a speed of 2 meters per second after moving a distance of 5 meters. Find A, the acceleration of the lift, B, the tension in the cable if the lift is moving vertically downwards, C, the tension in the cable if the lift is moving vertically upwards. So for A, the lift starts from rest. So our initial velocity U is 0. It also reaches a speed V of 2 meters per second after traveling 5 meters. We need to calculate the acceleration. So we are going to use equation number 4, V squared equals to U squared plus 2AS. Let's do our substitution. We get 4 because 2 squared is 4 equals to 0 plus 2 times A times 5. This reduces to 4 equals to 10A. And solving gives us 2 over 5 meters per second. So the acceleration is 2 over 5 meters per second. For B, we need to do a sketch. So this is the lift. The total weight of the lift is 1000 G newtons. There's also tension T in the cable, and this particular lift is moving downwards. So we're going to use Newton's second law of motion, F equals to ma. In this case, the resultant force moving the lift down will be the 1000 G Newton force, which is the weight, minus the tension in the cable. So, in this case, F resultant force is equals to 1000 G minus T. That means 1000 G minus T equals to the mass, which is 1000 kilograms, times the acceleration that we just found, 2/5. So we get this. We can reduce a fraction. 5 goes to 1, 5 goes to 200. So the equation reduces to 1000 G minus T equals to 400. Rearranging will give you T equals to 1000 G minus 400. And evaluating gives us 9400 newtons. For C, we do a similar diagram. The lift again has a total weight of 1000 G newtons, and there's tension T in the cable. By this time, the cable is moving up. So in this case, the resultant force, that is moving the lift up with the tension minus 1000 G newtons. That means T minus 1000 G is equals to the mass, which is 1000 times 2/5. So we get this equation. We can reduce the fraction to get 200 here. And the equation reduces to T minus 1000 G equals to 400. Rearranging will give you T equals to 1000 G plus 400. And finally, evaluating gives us 10,200 newtons. Question 3. The engine of a car cuts out when it is moving along a straight horizontal road with a speed of 20 meters per second. The car comes to rest without the brakes being applied. In a model of the situation, it is assumed that the car is subject to a resisting force with constant magnitude of 250 newtons. A. Find how long it takes the car to stop. B. Find how far the car travels before it stops. So for A, so let's do our sketch. This is the car, and this is a straight horizontal road. And the car is moving in this direction. But because the engine has cut out, there's no force pulling the car in this direction. It's only moving in this direction because it was initially moving at 20 meters per second. So the only force acting on it horizontally is a 250 Newton force. And that's why the car will come to rest, because the 250 Newton is opposing the motion, and it will bring it to rest gradually. There's a weight acting, and because of that, there's a normal reaction R. These two forces, though, will not have any effect on the motion in this direction. And because the car is not moving up or down, we will not also use these two forces in our calculation. So the only force acting on the car horizontally is a 250 Newton force. So the car is initially moving at 20 meters per second. That means U is 20 meters per second. It will come to rest. So it means V equals to 0. We need to find the time. But before we can find the time, we need to find the acceleration. Now, to find the acceleration, we are going to use Newton's second law of motion, which states that F equals to ma. The only force acting on this car horizontally now is 250 Newtons, and it's opposing the motion. So it means it's going to be minus 250 is equal to 500 times A. Rearranging and solving will give you minus half meters per second squared. Please note that the acceleration is minus 0.5, but when you are asked to state the deceleration, it's going to be positive 0.5 meters per second. Now that we have got acceleration, we can go and find the time. So the two-variable equation that we are going to use is the first one. V equals to U plus AT. V is 0, U is 20, and A is minus a half. So rearrange you're going to get half t equals to 20. Solve, I'm going to get t is equal to 40 seconds. For B, there are 3 ways you can find the distance traveled. I'm going to show you all the 3 ways. But in exams, you don't need to do all 3 ways. One will be enough. So the first one, you're going to use equation 3 to find s. We've got u, we've got t, we've got a. So we do our simple substitution to get s equals to 20 times 40 minus half times a half times 40 squared. Do some factorization and solve, and you're going to get 400 meters. We could have also used v squared equals to u squared plus 2a. Again, we do our substitution to get 0 squared equals to 20 squared minus 2 times half times s. This 2 will cross out this one, and this will reduce to 0 equals to 400 minus s. Solve for s, you get 400 meters as before. We could have used yet another formula. Equation number 2, s equals to half brackets u plus v times t. We do our substitution, and we get half brackets 20 plus 0, all of that times 40. 2 goes a 1, 2 goes a 20. So we end up with s equals to 20 times 20, and that gives us 400 meters, again, as before. So this is the end of exercise 10.3.